Hello, I'm Nathaniel. Today we will now talk about crazy fraction representations. Wait, but they're not as crazy as you might expect, because they're actually very elegant ones in fact. Continued fractions and the Stern-Brocot tree. You see how they are related in this video. Let's talk about continued fractions. This is a simple continued fraction. There are also complicated continued fractions where the ones are replaced by actual numbers, but that's not actually very elegant representation. So let's move on. In mathematics, this is written more clearly as A, B, C, D, E. This is why the bracket notation is easier, because if you spend your whole life writing ones, you might be only at 100,000. Well, if you use bracket notation, it can be a lot longer and a lot more compact. And I can go further to say this is more elegant than decimal representation. We'll see why. All fractions terminate and all quadratic irrationals are recurring. For example, take this irrational, and this has a continued representation of this. The converse of all quadratic irrationals are recurring is also true. If it's recurring, and the continued fraction expansion is recurring, then it's a quadratic irrational. This is why you should learn to tame quadratic irrationals into continued fractions. No matter how crazy your quadratic irrational, it will still be a recurring continued fraction. You can use Wolfram alpha if you want. Let's talk about the Stern-Brocot tree. This is a tree of fractions generated by this operation, called Jacobi addition of medians. You might have made this mistake when you want to add fractions. Well, this middle fraction called the medians is always between the two fractions that you want to add up. And we see how this operation can be used in a surprising way. Start with 0 over 1 and 1 over 0. The median on this is 1. Finding the median on this with the two other fractions 0 over 1 and 1 over 0 gets half and 2 over 1. Continuing on this process will give you this tree. Isn't that amazing? The one that's called the Stern-Brocot tree. It is a tree. And now here's a theorem. Every positive rational number except 0 over 1 and 1 over 0 can be expressed as a series of L's and R's from 1 over 1. For example, let's say you want to pick 7 over 5. We have our Stern-Brocot tree here. Take R, go to 2 over 1, take L to 3 over 2, take L to 4 over 3, and take R to 7 over 5. We write this string as RLLR, starting from 1 over 1. Now what's the connection? It's very surprising. Let this notation be true. R to the power of n be a series of n r's and L to the power of n being a series of n l's. In a fraction, it can be expressed as this. The continued fraction is this. You see how the coefficients fall down? Similarly, if there is no L at the end of the fraction. These can also be used when there is no R on the left of the fraction, therefore having a 0 integer part. Now isn't that elegant? Thank you, and see you in my next math video. And don't forget to stay sync when I come back.